All right, so we've spent some time doing translations in predicate logic, but we've done that without a formal understanding of the language or its formation rules. So I want to spend a little bit of time on this before we move into the semantics of predicate logic. The slides I'm going to show you right now are actually from the lectures that you should have engaged already. So really, I'm just revisiting this and emphasizing certain key features that the lectures might be a little generic about. So one thing that's really important to understand is that predicate logic, and in fact, everything else that we're going to look at this semester, is some kind of extension of propositional logic, okay? So we never actually are going beyond propositional logic in the sense that we don't use it any more than we have abandoned, say, simple arithmetic when we do calculus or differential equations. So that means when we look at the actual definition of the vocabulary of predicate logic, it begins with sentence letters. And what that tells us is that propositional logic is still with us. And specifically, what that actually means is that we can mix, technically, we can mix propositional logic symbols with predicate logic symbols. So, in other words, a formula like f of a or q is actually a perfectly good predicate logic formula. And we actually will do that sometimes if we're translating things, because occasionally you'll hit a sentence that is just beyond the resources predicate logic to unpack. Predicate logic is still really, really simple. And so when we encounter something like that, we might just say, oh, well, I don't know. I mean, this is just not translatable into predicate logic, so I'll just go back to propositional logic and label the whole proposition Q or R or whatever. So because we still have propositional logic in the system, when we're really being technical, what we say is that we confine propositional logic symbols to P, Q, R, and S, and then P1, Q1, etc., with subscripts Q, P2, Q2, P3, Q4, etc. And that gives us an infinite amount of those. And then we confine our predicates to A, B, C through O, and also give them subscripts as well. Now, in practice, we don't really do this. We just need to know that we can. The reason we don't do it is because sometimes it's just more intuitive to grab a P or a Q or an R and make it the name of a predicate. Okay, and so then we have names, as we know, and we have individual variables. We designate them to specific parts of the alphabet. Then we just have the sentential connectives from propositional logic. We have our two new quantifiers, and we have brackets. Formally, we only acknowledge these brackets, but informally, we acknowledge square brackets, which we might use sometimes when formulas get pretty complicated. Okay, so that's the actual full definition of the predicate logic vocabulary. And so now we just want to make sure we understand the formation rules. So the formation rules haven't actually changed that much. So we just add one to it after 3. 5 is just the same as 4 used to be with propositional logic. But what you have to understand is that now, when we look at the first rule, any atomic formula is a woof, we're talking about, we've expanded our notion of what an atomic formula is. So in addition to being, say, P or Q or R, we also have atomic formulas from predicate logic, and these would be ones that are simply a predicate together with a name, right? So it could be FA, it could be GB, and it can also be more than one names if we're using predicate two-place predicates, three-place predicates, so we could have R, A, B. These would all be atomic formulas in our expanded understanding of the language. All right, so Rule 1 still just says then, any atomic formula is a woof. And Rule 2 just says if something is a woof, then not that something is a woof. And as you know, the important part about that is that when you add a negation, you don't add parentheses. And that's not the statement that you don't have to add them. That's a statement that you do not add them. Now, of course, this is just our system. Other systems do have you add parentheses, but we're speaking the system. And so you just have to know what the rules of this system are. Okay, and the third rule is exactly the same as well, right? So if two things are formulas, then you can put them together with any of the binary operators, and you have to add parentheses. It's not that you can, it's that you have to. Now, of course, this is for making official woofs. We don't always do that, as you know. We often adopt the convention of dropping the outside brackets, but that's not something that belongs in the formation rules of the language itself. So, as I said, number 4 is the only new rule. So let's look at what it says. If you look at the textbook on this, it's going to be using Greek letters, which is conventional, but I try to avoid that because I think it's just kind of annoying. So it says if AC is a formula, A, of course, is a predicate letter, any predicate letter, and C is any name. So if AC is a formula with name C, and V is a variable that does not occur in AC, then there exists a VAV, and for all VAV are formulas. Now, what does that say? Well, just look at a specific instance. Suppose you know that, say, let A be F, and let C be A, okay? And so that's an atomic formula. And so what we're being told in this Rule 4 is that if you have an atomic formula of this kind, then if you want to, you can substitute a variable for A and put directly in front of the formula either an existential or a universal quantifier with the same variable, okay? So this isn't inference, remember. This is just telling you how you can construct something that's a woof, okay? So if we know that FA is a woof, which we do because it's an atomic formula, then we can substitute a variable for A, like say X, and we can write there exists an X, F of X. Excuse me, hope you caught my mistake there. It's F of X, okay? Or you could also have said for all X, F of X, or for all Y, F of Y. Those are the two things that you would be allowed to do in respect to our two new quantifiers. So notice again, it did not involve the addition of parentheses. And again, that is not, you don't have to add parentheses. It's that you do not add parentheses. And that, believe it or not, is all there is to it. This is kind of deceptive in that it really doesn't seem like it contains enough information to let you figure out whether any predicate logic formula at all is a woof. But as a matter of fact, it does. And so let's just finish by proving that to ourselves. So suppose we started with something like for all X, Fxx, and you're asked, is that a woof? Now, you might just eyeball it and say, oh yes, of course it's a woof. But how would you prove that it's a woof? All right, well, the answer is that you would begin with atomics, just as we did in propositional logic, and try to build it. So X and strongly suggests that you want to use the same names, but actually there's no rule that says you have to, right? And because of this, if you make a poor decision, you might end up concluding that something is not a WOOF when it is, right? So if, for example, you said, well, let's start with FAB, and then I know by rule 4 we can go for all X, FAX, substituting X for B, but now, that's not the original formula, so it's not a WOOF. Well, right, not by this procedure, but by a different procedure, we might come up with a different answer, and it's surely one you've anticipated. Suppose you were to start with FAA. And then, of course, rule 4 tells you you can substitute the variable for both occurrences of the name, and you get for all X, F, X, X, and that proves that it is a WOOF. Now, notice what if the question had been whether for all X parentheses F, X, X is a WOOF. Then you'd start with FAA, and you would say, well, look, there's no rule that allows me to put parentheses around FAA, so it's not a WOOF. If you were asked whether for all X not F, X, X is a WOOF, then you would start with FAA by rule 1, negate FAA by rule 2, and then by rule 4, go to for all X not F, X, X. Suppose you were asked if it's not the case that for all X, F, X, X, with parentheses placed here, is a WOOF. What would you do? Well, FAA for all X, F, X, X, rule 3, and now what? You're stuck because there's nothing that allows you to put parentheses, so that's not a WOOF. So how about for all X, there exists a Y such that F, Y, Y. So as I said before, normally it'd be pretty obvious that you'd want to start with FAA, but if you ignored the obvious and started with FAB, you could still try to build the formula, and you could say because FAB is, after all, an atomic proposition. So rule 3 is definitely going to allow you to write there exists a Y such that, say, F, Y, B, so far so good. But now, of course, you have to add for all X, right? And when you add for all X, sorry, let me be explicit about this, for all X, right? And that means you have to put an X in for B, and that's not that formula. So that didn't work. Well, let's try to do it in the intuitively correct way, starting with FAA. So you could still go, there exists a Y, F, Y, A, and then of course you'd run into exactly the same problem. And you could also go from FAA to there exists a Y, F, Y, Y, substituting the variable Y for both occurrences of A. But now, how do you get the for all X in there, right? You can't just slap on another quantifier. You can only add another quantifier if you are substituting this variable for some name in the formula. Okay, well, how about for all X, there exists an X such that F, X, X. Is that a formula? Well, start with FAA. You can certainly go from there to write there exists an X, F, X, A. So that's a formula. But now, can you write as your next step for all x, there exists an x such that f x, and the answer is no, you cannot. And why? Well, it's because Rule 3 required the variable x not to already exist in the formula. So that's very important. So I said we could combine propositional logic formulas with predicate logic. So, for example, for all x, there exists a y such that f x y, then p or g of a. So that's by good old Rule 3. Okay, so what else can we do? Well, we can't add this conditional in yet because that would require us to instantly put in 2 more brackets. So now we have to work on this over here. We already know how to do that. Let's start with, say, FAB, right? And then by Rule 4. So notice this has a little bit different feel for it, right? I mean, we're just throwing in an atomic formula to see if we can build this up, which is not, there's no correlate of that in propositional logic, just throwing in whatever atomic formula we feel like. All right, and so then Rule 4 is going to tell us that we can do exists a y, f a y, and you can sort of bring down your p or ga, right? And then Rule 4 is going to tell us that we can do for all x, there exists a y such that fxy, and then again you can bring down your p or ga. Okay, so again, so far so good. And then finally, add a conditional brackets by Rule 3. And once again, we've replicated the formula, and so we know that's a woof. Okay, so this really isn't difficult. You just have to know the rules and apply them. You need to be patient, of course. It's easy to get lazy and just trust your eyeballs. And I do that, admittedly. And sometimes even after doing logic for 30 years, I'll make a mistake. All right, so let's just look at a couple more. Suppose we consider there exists an x, f of x, or there exists an x, f of x, with parentheses. All right, now, is this a formula? Go ahead and formulate a guess about that, see if you're tracking. Okay, so it's pretty easy to show that it is. Let's say FA, right? Or I could also write FA or FB, right? It doesn't matter, it's going to work out the same either way. Okay, and then, so what do I want to do? Well, I've got 2 atomic formulas here. Rule 4 tells me that I can write there exists an x fx, right? Bring down the FB. Rule 4 again tells me I can write exists an x fx, right? And then Rule 3 tells me I can put them together with a wedge and parentheses. So if you guessed this wasn't a formula, it's because you saw the variables reoccurring, but that's not against the rules. You just have to make sure that you can build it using the formation rules. Now, if you want to talk more sort of intuitively and abstractly, the reason this is a formula is because this quantifier only has scope over this predicate, and this quantifier only has scope over this predicate. So let's look at a variation that would not turn out to be a woof. So let's say for all x, there exists an x, f x, or gx a. Okay, so let's build the formula. Let's start out with FA here, and let's start out with GBA So rule 3 tells us that we can write there exists an x f of x, bring down the GBA, that's fine, and then we can put these together. Excuse me, there exists an f of x was by rule 4, I might have said rule 3. So we put them together with a wedge by rule 3. And then finally, what we want to do is add in for all x. But we have to stop dead in our tracks, right? Because we can't do x because x is a variable already in the woof. So what we would have to do, and this is of course no longer the formula, but we would have to do is something like for all y, there exists an x fx or g y a. Okay, so this is a formula, but it's not that formula. So the original one is not a woof. And so finally, just because I didn't make it clear earlier, even though it's something you think is pretty obvious, take something like there exists an x f of a. That's not a woof, right? Because well, let's just make it clear why. Because if you start with f of a, then if you want to add a operator, you have to add in the variable. So you'll never have well-formed formulas where you have a quantifier with a particular variable and that variable not occurring in the formula. And as I mentioned in the past, you will never have free variables. So for example, for all y, there exists an x, there exists an x fx if and only if f x a, right? So let's see what's wrong with this. Well, in the beginning it seems fine. We can start with, say, f of b, and we can start with, say, f c a, okay? And then by rule 3, we can go to there exists an x f of x, which captures that, right? And we can just bring down the f c a with a biconditional like that. But then we're stuck, right? Because if we add on for all y, there exists an x fx, if and only if, it's got to be y that goes in for c, f y a. Okay, so hopefully you see it's still a very mechanical procedure, just a slightly more complicated one in virtue of the addition of Rule 4 for managing the predicates. The important thing, the really, really important thing to understand is if you're asked why, or if you're asked whether something is a woof or not, and you say yes it is a woof or no it is not a woof, and then you're asked why, there's only one answer to that. There's really only one answer. The answer is, in the case of yes, because it can be built using the formation rules. And then you just show how. And if the answer is no, it's because it cannot be built using the formation rules. And you just show why not. That's all there is to it. There's no other way to do it. Well, when I say no other way, there's no other perfectly precise way. And you should be perfectly precise when you do this. Okay?